All right. The regular coordinate system that we learned using x and y to represent points, represent locations in 2D is called Cartesian. So for example, 2, 1 means you go 2 steps to the right and you go up by 1. The word Cartesian comes from the name Descartes. He was a philosopher, most famously known for his comment that I think, therefore I am. He spent a lot of time thinking in his bed, and the legend says that one day he was again just laying down in bed thinking about life and philosophy, and there was a fly on the ceiling just going ring, ring, like that, and then he was thinking about how to use mathematics to describe the position of the fly, and that's how he came up with his coordinate system. So that was called Cartesian coordinates. Well, it turns out that sometimes this way of describing position is not the best. Sometimes you want something else. And that's what I'm trying to talk about today. So there's another way to talk about the position of the fly, or a position of a point in the plane, which is called the polar coordinate system. And it works like this. First, you have to pick an angle. And then you have to decide the distance from the origin. And this thing here, this point here is represented as r comma theta. That's called the polar coordinate system. Okay. Now, usually people don't write anything to distinguish this and that, but if it's hard to know which one's which by the context, then you might want to put something extra. So sometimes people write down 2, 1 with rectangular, and sometimes they write down r comma theta with POL, just to distinguish those two. Okay? But usually when the given context is clear which is which, they don't write anything at all. Okay? You have to just figure out which is which. Okay? All right, so let me give you an example. So here's the first example. Convert to rectangular coordinates. Rectangular coordinate system is another name for the Cartesian coordinate system. They're the same thing. Let's say you're given, say, 6 comma pi over 6. And this pi over 6 kind of tells you that, oh, this is like a polar coordinate system. Okay? If you change this to rectangular, what would it become? That's the question. And this can be thought geometrically. Let's draw the graph. Pi over 6 in degrees is what? 30, right? Pi is 180. 180 divided by pi radians is 180 degrees. 180 degrees divided by 6 is 30. So you have this ray of 30 degrees. And then on this ray, you're going 6 steps. And you reach this place. So definitely, this is a description of a position in the plane. Now the question is, if you were to describe the same position using rectangular, what will be the coordinate of this position? And then we can use trigonometry here, right? So you use SOHCAHTOA. So if I say this is x and that's y, if I use SOHCAHTOA, sine of 30 is, yeah, the value is 1/2, right? But that's 1 over what in this picture? SOHCAHTOA is,
So 3.
so it's opposite, which is y, right, over hypotenuse, which is 6. And then if you solve, if you take this 1/2 equals to y over 6, you do cross multiply. You cross multiply, 6 is equal to 2y, and then y is equal to 3. So we find that the y coordinate is 3. Now to get x, what should you use? You can use Pythagorean theorem, you're right. You can now use Pythagorean theorem, because now you know two sides of the right triangle. But usually people use cosine, so you can use cosine 30 degrees, which is actually radical 3 over 2, and that's equal to what in this picture? X over 6, okay? Because cosine is adjacent over hypotenuse. So x will be 3 radical 3 if you solve this. So the answer to this is what comma what? 3 radical 3 comma 3. So that's how you go from polar coordinate description to rectangular coordinate description. Yes?
Are they always going to be given in radians, or will they be given in degrees?
It can be given in degrees.
Do you have to convert to radians to solve? Or?
No.
Okay.
Now, radians is our preferred measure of the angle, but if you write down degrees, you have to have this small circle on the top right. I've noticed that some of the engineering professors forget about those small circles on the top right.
Like some here.
Huh?
Wait, who?
I don't know. I've seen people write that. If you see that, tell them you should write that small circle, or else it's wrong. It's just as bad as not writing units in physics. All right. Okay. Now, we don't want to be doing SOHCAHTOA all the time, so let's try to come up with the formula for converting them. Okay. So here's the formula. If I'm giving you position of a point given by r comma theta, then to get the x and y, you have to use SOHCAHTOA. But if you look at what's happening here, for x we use cosine, for y we use sine, right? And that's what we have to do. For x we need to do r times cosine of theta, and for y we need r times sine theta. So this formula tells you how to take the coordinates given by r and theta and convert it to the x and y coordinates. Now to go back, if you're given x and y and you want to go back to r and theta, what would you do? Well, so think about this. If you're given x and y and you have to find r, what would you do?
X squared plus the square root of x squared.
R would be square root of x squared plus y squared. Right? What about the angle theta? You have to do y over x and take the inverse tan, and inverse of y over x. Now for us this is very easy because we've already done this when we were doing the polar representation of the complex numbers, right? So it's, in a sense, we already did this when we were doing the complex numbers for polar. Now, the tangent inverse only gives you numbers between negative 90 degrees to positive 90 degrees. So it detects the angles correctly when it's on the right side, when the angle is in the fourth quadrant or on the first quadrant. But if you're on the second quadrant or the third quadrant, it gives you the wrong answer. It's off by 180, right? So to correct that, you need to put plus alpha where this plus alpha is. On the right side, you don't have to do anything. It's all correct. But on the left side, you want to add 180 degrees to correct. Okay. Now, the usual convention is that you add 180 in the third quadrant, no, second quadrant, but subtract 180 in the third quadrant. This is done so that the answer that you get is always between negative 180 degrees to positive 180 degrees. Okay? So that's the standard thing that they do. However, there's another convention that's just as good. The other convention is to use 0, 180, 180, and then here 360. This is another convention. Now, I'm mentioning this first because I saw that often in engineering department, they want the angles to be between negative 180 to positive 180. Usually for mathematicians, somehow we prefer the angles to be between 0 to 360. So if you follow this convention, your angle falls between 0 to 360. Okay?
What do you
And
want
then-
on the test?
Hmm?
What do you want on
Either one will be accepted as correct. Okay? All right. Now, what's interesting is to actually use these to take an equation in rectangular form into polar coordinates. So here's an example. Alright. So let's think about y equals to 4. What kind of graph does this have? Y equals to 4. Horizontal line. Okay. 4. Like that. Now what would happen if you change this into polar coordinate equation? Well, equation in polar coordinates means that you're not going to use x and y, you want to use r and theta. Right? So instead of having y, what do you want to put? So in polar, this is r sine theta equals 4. But just as when equations are written in the rectangular, usually you want to write in the form of y equals the function of x, right? So you want to do the same thing here. You want to solve for r and say r equals a function of theta. It's 4 cosecant theta, because 1 over sine is cosecant. So here's an interesting result. It's saying that if you were to plot r equals to 4 times cosecant of theta, you actually get this line. Now, let me show you another one which is more obvious than the first one. Think about x squared plus y squared equal to 4. How would you convert this into polar? You see x, what do? Replace it by r cosine theta. Which is same as r squared equal to r squared cosine squared theta plus r squared sine squared theta equal to 4. And you can factor the r and get cosine squared theta plus sine squared theta. What's cosine squared plus sine squared? 4. So you get what? R squared equal to 4. If you solve this, you get r equals to 2, or r equals to negative 2. And just as in the rectangular, we could have just x equal to something or y equals to something. In the polar coordinate system, we can have r equals to a number. Now, it turns out that if we really knew what the geometric shape of this thing is, we didn't have to go through all this math. What's the shape of this thing? It's a circle of radius 2, because 2 squared is 4, right? So this represents the graph, a circle with radius 2. Now think about all the points on this circle. What's the distance from the origin? 2. So if you just set r equals to 2, what are you going to get? All the points that are 2 away from the origin, so you're going to get the circle. Isn't that right? So just this is enough. Okay? Now, although this is not usually done, this is correct too. You can write r equals to -2, and that will always, again, be a circle. It's just a strange way to write down the circle of radius 2, but this is what it means. For any ray, instead of going to the positive direction, you go backwards by 2, 1, 2, and you plot. Okay? And if you take all the rays and you start plotting the -2's, you again get the same circle. Okay? So that's another way to say the circle, but just one is enough. So if you convert this into the polar, you can just say r is equal to 2. And this already shows us some possibility of this polar coordinate system. See, polar coordinate system is horrible at expressing lines, right? But it's great when you try to express circles. It turns out that when it comes to expressing integrals over circles, when you go to the polar coordinate system, it becomes better. Okay? So that's what we're going to do the next time. I'm going to show you how to do integration over the polar coordinate system, and then I'll convince you how easy it is when you